Welcome to Pepper Pen Biology. Today I have chosen the topic which is one of chromatography techniques, that is ion exchange chromatography. Before digging into this, I encourage you to watch other tools and technique videos of this channel. Please share your views or suggestions with me. Subscribe for more videos like this. So let's learn. These are some points I am planning to cover in this video. First, definition of chromatography, concepts behind this process, essential terminologies of these techniques, types of chromatography, and finally discussing about ion exchange chromatography. The books I followed for making this video are this. You may go through these books for enhancing your basic knowledge regarding biochemical techniques. For a biochemist, it becomes difficult if interacting molecules in any biological process are not well explained through its structure or characterizations. To know molecular nature of life processes, isolation of molecules is essential. So, chromatography is one of such techniques by which separation and purifying of biomolecules is possible. Russian botanist in 1902 developed this groundbreaking technique. His studies on the isolation and characterization of the colorful pigments in plant chloroplast. He prepared separating columns by packing fine powders like sucrose and chalk, that is calcium carbonate, into long glass tubes. He then poured petroleum ether-derived extracts through the columns. As continued eluting the columns with solvent, he noted the formation of yellow and green zones. For these color bands, he chose named for the method. Greek chroma meaning color and graphene meaning writing. Chromatography is widely used as an analytical tool to measure biophysical and other quantitative properties of molecules. Concept behind this process is very simple. The sample to be examined is allowed to interact with two physically distinct entities, a mobile phase and a stationary phase. The sample most often contains a mixture of several components to be separated. The molecules are targeted for analysis are called analytes. The mobile phase, which may be a liquid or gas, moves the sample components through a region containing the solid or liquid stationary phase called the sorbent. The molecular components in the sample distribute themselves between the mobile phase and sorbent, thus have the opportunity to interact intimately with the stationary phase. If the molecules prefer to bind with the sorbent, they are retarded in their movement. If not, the molecules are easily removed or eluted from the system by the mobile phase. Okay, now we need to learn few useful terms of this technique. Eluent. An eluent is solvent used to carry the components of mixture through a stationary phase. It is an alternative term used for the mobile phase. Eluate. The mobile phase that exits the column is termed the eluate. Elution is a process in which solutes are washed through a stationary phase by the movement of a mobile phase. Chromatography represents a separation technique, whereas a chromatograph is a system for performing chromatography. The chart displaying the time-dependent change in signal intensity as a result of the separation is called chromatogram. Now it's time to know about three fundamental chromatographic methods. Based on shape of the chromatographic bed, based on physical state of the mobile and stationary phases, and based on the mechanism of separation. Based on shape, there are two types of chromatography: planar chromatography and column chromatography. In planar chromatography, the stationary phase is present as or on a plane. The plane can be paper in case of paper chromatography or thin layer of a substance sprayed on a glass, metal or plastic plate, as in thin layer chromatography. In column chromatography, the stationary bed is within a tube. The particles of the solid stationary phase or support coated with a liquid stationary phase may fill the whole inside volume of the tube or be concentrated on or along the inside tube wall, leaving an open, unrestricted path for the mobile phase in the middle part of the tube. Based on physical nature of mobile phase, there are two types of chromatography: gas chromatography and liquid chromatography, and they are also subgrouped as gas solid chromatography, gas liquid chromatography, liquid solid chromatography and liquid liquid chromatography. Based on mechanism, these technique can be partition, absorption, size exclusion, affinity and ion exchange chromatography, which we are going to discuss now. It is applicable for the separation of charged molecules. That is, we all know a particle, atom or molecule with net electrical charge. Positively charged ions are cations and negatively charged ions are anions. Ionic analytes display reversible electrostatic interactions with a charged stationary phase. Now the question is, how is it done? Typically, ion chromatography instrumentation includes pump, injector, column, suppressor, detector and a recorder or data system. The column is packed with a stationary phase consisting of a synthetic resin that is tagged with ionic functional group. These are the stages involved in ion exchange chromatography. In stage 1, the insoluble resin material, positively charged in the column, is surrounded by buffer counter ions. In stage 2, loading of the column brings analytes of different charge into the ion exchange medium. Solutes entering the column may be negatively charged, positively charged, or neutral under the experimental conditions. In stage 3, analytes that have a charge opposite to that of the resin bind tightly but reversibly to the stationary phase. The strength of the binding depending on the size of the charge and the charge density of the analyte. The greater the charge or the charge density, the stronger the interaction. Neutral analytes, or those with a charge identical to that of the resin, show little or no affinity for the stationary phase and move with the eluting buffer. In stage 4, the bound analytes can be released by eluting the column with a buffer or increased ionic strength or pH. In final stage, an increase in buffer ionic strength releases bound analytes by displacement. Increasing the buffer pH decreases the strength of the interaction by reducing the charge on the analyte or on the resin. Now we will focus on the ion exchange resins, selection of experimental conditions and application of ion exchange chromatography. Ion exchange are made up of two parts, an insoluble three-dimensional matrix and chemically bonded charge groups within and on the surface of the matrix. The resins are prepared from a variety of materials including polystyrene, acrylic resins, polysaccharides, that is dextrans, agarose and cellulose. An ion exchanger is classified as cationic or anionic depending on whether it exchanges cations or anions. A resin that has negatively charged functional groups exchanges positive ions and is a cation exchanger. Each type of exchanger is also classified as strong and weak according to ionizing strength of the functional group. An exchanger with a quaternary amino group is therefore a strongly basic amino exchanger, whereas primary or secondary aromatic or aliphatic amino groups would lead to a weakly basic anion exchanger. A strongly acidic cation exchanger contains the sulfonic acid group. This table shows ionic exchanges according to each of these classifications. These are anion and cation exchanger with functional groups, used matrix and the class it belongs. Okay, now we approach for the selection of the ion exchanger. The nature of molecules to be separated must be considered first. For relatively small, stable molecules like amino acids, lipids, nucleotides, carbohydrates, pigments, etc., the synthetic resins based on polystyrene are most effective. They have relatively high capacity for small molecules because the extensive cross-linking still allows access to the interior of the resin beads. For separations of peptides, proteins, nucleic acids, or polysaccharides and other large biomolecules, one must consider the use of fibrous cellulosic ion exchangers and low % cross-linked dextran or acrylic exchangers. If the analyte has only one type of charge group, the choice is simple. A molecule that has a positive charge will bind to a cationic exchanger or vice versa. Many molecules have more than one type of ionizing group and many have both negatively and positively charged group, like they are amphoteric. The net charge on such molecules depend on pH. At the isoelectric point of substance has no net charge and would not bind to any type of ion exchanger. The figure shows how the net charge of a hypothetical protein changes as a function of pH. Below the isoelectric point, the molecule has a net positive charge and would be bound to a cation exchanger. Above the isoelectric point, the net charge is negative and the protein would bind to an anion exchanger. The ion exchanger charged with the macromolecule is treated with buffers of increasing ionic strength or changing pH. Buffer ions with a charge opposite to that on the ion exchanger compete with analyte for binding sites and greatly reduce the capacity of the column. Cationic buffers should be used with anionic exchangers, and anionic buffers should be used with cationic exchangers. An important use of ion exchange chromatography is in the routine analysis of amino acid mixture. The 20 principal amino acids from blood serum or from the hydrolysis of proteins are separated and used in clinical diagnosis. This is the most effective method for water purification. In the analysis of products of hydrolysis of nucleic acids, chelating resins are used to collect trace metals from seawater and to analyze lunar rocks and rare trace elements on Earth. This is all about today's video. I hope you can get clear idea about ion exchange chromatography. I'll be back soon with another video. Till then, stay with Paper Pen Biology. Thank you for your patience.